Thanks everyone for coming to attend this session, which is yet another in the series of Scream presentations after the Gordon Bell. And so today we have Peter Bogenshutz, who's going to talk to us about simpler ways of running the Scream model. And Peter has a long history of atmospheric science research. He got a bachelor's degree at Embry-Riddle Aeronautic University, and then went on to Florida State, where he got a master's degree, and then went to Utah State, where he got his PhD. And he has been working at the interface of clouds and turbulence and convective motions for most of his career. And so we're going to hear some of that today.
Alrighty, thank you, Peter. And just one minor correction: I went to University of Utah, not Utah State. That's sacrilege. But anyway, thank you all for being here today. I'm excited to talk about this work. And I also want to note that this work represents the culmination of efforts from many, certainly not just me. And in many cases, I'm just a reporter here, and names will be dropped on individual slides and via paper citations for the relevant acknowledgments. So at this point in the series, I trust that we all know what the award-winning Scream model is. You've probably been thinking throughout this whole series of talks that you probably don't have the computational resources to run Scream. But guess what? I run Scream at cloud permitting resolutions probably every day, sometimes all day, with multiple simulations going at once, while barely making a dent in the computational allocation. And you can too. Today, I will present on two configurations of Scream that can make this possible and how they are scientifically useful. Next slide, please. So what is displayed here is an animation made by Zhefang of the very first global simulation of Scream V0, which I still consider to be the coolest animation made from a Scream simulation. Though this maiden voyage simulation is a bit old at this point and run with the clunky Fortran code, much of the simulation characteristics still hold. So watching this animation go, we can see several features being resolved, such as tropical cyclones, organized thunderstorm complexes, and precipitation being induced by topography. One feature of the simulation that probably pops out to you is the convection in the tropics, which is known as our popcorn convection problem that has plagued us since day one and still continues to do so to this day. This popcorn problem is characterized by an abundance of smaller than observed precipitation clusters. Now, when we first ran the simulation and noticed this problem, myself, as a Scream parameterization developer, I was dying to do a myriad of sensitivity experiments, both parametric and structural, to try to understand what makes this popcorn problem tick. But you know what? I couldn't. Running global convection permitting simulations, even with performance optimized code, is just too expensive to run, even for short duration realization simulations for the common scientists like myself. So it became very obvious early on in the Scream project that still enabled us to run at convective permitting. So I'm happy to report that now we have two such configurations, both of which I will discuss today. The first is the regionally refined, or RRM configuration, of which the functionality was largely inherited from E3SM. In Scream RRM, a small portion of the globe has convective permitting resolution, while the rest of the globe has resolution typical of DPM. I will speak to this configuration in the second half of the talk, but in short, you can think of Scream RRM configuration as being a proxy for a limited area model or a high-resolution regional climate model. The configuration I will talk about first is one which I developed myself with significant and crucial contributions from Chris Eldred at Sandia, known as Doubly-Periodic Scream, or DP Scream. DP Scream represents a three-dimensional cloud-resolving model on a planar grid, and you can think of DP Scream as serving the role that a single column model would play in a GCM that is used to study the model at the process level. Now, I'm not going to argue that one of these configurations is better than the other. I personally use both on a daily basis. Each has their own niche, and the two configurations are complementary to each other, and both are essential support configurations for Scream to aid in development and evaluation of the model. In addition, if you personally run Scream in the foreseeable future, chances are high that you will probably be running one of these two configurations, as running the global model demands too high computational resources, unless, of course, you win a massive allocation award. Next slide, please. So first, let's talk about DP-Scream. This configuration was developed to fill the need for an efficient configuration, similar to a single column model where users can get running out of the box with negligible computational resources. DP-Scream is characterized as a single point three-dimensional cloud resolving model on a planar grid. By single point, I mean that the entire domain assumes homogeneous surface type, topography, and location, even though there are multiple columns. We provide support and scripts for over 30 cases, and with DP-Scream, it is possible for anyone to get up and running within 10 minutes after watching this presentation on any machine that E3SM runs on, and I will be providing links at the end of the talk. A novel feature of DP-Scream is that the user has complete freedom to modify domain size and resolution by setting nameless parameters. This is unlike the global model, or RRM, where making such modifications is time-consuming and requires some level of experience points. And here I've listed the cost comparison of DP-Scream v0 versus Scream v0, where you can see that the cost of running DP-Scream in a standard domain size is 4 orders of magnitude less than running the full model. And it's something that virtually anyone can afford without giving it a second thought. I'm also happy to report that DP-Scream v1 is now in its initial testing stages as of last week, thanks primarily to the hard work of Conrad Clevenger, and will eventually replace the Fortran version, probably sometime within the coming year. So what can DP-Scream be used for? Next slide, please. So the first thing that I used it for was to study the resolution sensitivity of Scream, since as I already mentioned, changing the resolution and domain size is trivial in this configuration. In this example, we simulate a marine stratocumulus case, which was the basis for an LES intercomparison study led by Bjorn Stevens back in 2005, which featured an unusually large spread in the participating LES, as displayed in the black curve and the gray shading. The DP-Scream simulations, on the other hand, denoted by the colored curves, which were run with resolutions ranging from 100 meters to 5 kilometers, shows far less spread than the LES ensemble and shows good agreement with observations. This is particularly impressive because this range of resolution spans the gray zone of boundary layer turbulence and highlights that Scream is reasonably scale insensitive, at least for this regime, and though not explicitly shown on this slide, also scale aware, and can be run at higher resolutions than the default 3-kilometer model with no code modifications required. This is insight that would have been prohibitively expensive and difficult to obtain using the global model. It can help us guide future resolution choices in both RRM and the global model. Next slide, please. So another important application of DP-Scream is using it to replicate and understand systematic cloud biases in the global model. It was shown in the Scream v0 paper that Scream struggles to simulate shallow cumulus, as these clouds are typically too shallow in depth and more closely resemble stratocumulus, as seen on the figure on the left-hand side of the screen when compared to observations. On the right-hand side of the screen is a replication of this problem using DP-Scream. The top left panel represents the observations from a composite of Golden Day shallow convective cases at the Southern Great Plains site. This is a case that was developed by Yunyang Zhang. The DP-Scream simulation at the default resolution lies on the bottom left panel. And though DP-Scream 3-kilometer can adequately simulate the low-level cloud amount, perhaps even better than the higher resolution models, it is obvious that DP-Scream underestimates the vertical extent of these clouds by nearly 1 kilometer, which has side effects when trying to simulate the transition of shallow to deep cumulus. On the bottom right panel, we have a DP-Scream simulation where the resolution is increased to 100 meters, and we can see that this vertical extent problem is largely ameliorated. Unlike the stratocumulus example, which I previously showed, this is a regime where Scream is not scale insensitive, and the fact that the results improve as resolution increases provides clues that subgrid scale physics is likely the leading culprit here. Due to the very low computational cost of DP-Scream, the thread team is using machine learning for this case to determine if finding the optimal tuning parameter combination can reduce the biases associated with shallow convection. Next slide, please. So at the beginning of this talk, I mentioned the popcorn problem is one of the most glaring biases in Scream simulations. Here I am showing an animation from a DP-Scream simulation that I will be submitting to the second radiative convective equilibrium intercomparison project later this year. The RCE-MIP2 protocol represents a Mach Walker circulation setup with non-uniform SSTs, as shown at the bottom of the slide. The top panel represents the total precipitable water. Now, as the simulation integrates, we do see that SCREAM eventually aggregates the areas of convection into preferred regions, probably around day 30, 35. Looks like it's already gotten there. However, within these aggregated pockets, we see an abundance of small blips, speckles, or clusters, things that kind of look like fireflies dancing in the night, that really fails to ever really organize, which continues for the duration of the simulation. This is our popcorn convection problem, and Chris Try has previously demonstrated that the popcorn clusters produced in the DP simulations are statistically identical to the ones seen in the global model. In fact, a couple years ago, we used DP Scream as one of its first science applications to identify one of the causes of popcorn convection and managed to reduce popcorn populations by nearly 20%, using a workflow that would not have been computationally feasible using the global model by itself. However, as we can see, the problem still remains, and it's something that we continue to try to understand using DP Scream as our principal tool. Next slide, please. So in the interest of time, we move on to our next efficient configuration of Scream, known as Scream RRM. So unlike the DP configuration, the Scream project did not develop the RRM functionality, as this functionality was inherited from E3SM, thanks to the hard work by Chi Tang primarily. So as a refresher, a depiction of the CONUS RRM from E3SM v1 is depicted on the right panel. RRM allows for a region of interest on the globe to be refined at the cost. The cost of RRM is proportional to the size of the refined mesh. So as an example, let's say that your refined mesh size covers approximately 10% of the globe, then the cost of your RRM grid will be approximately 10% the cost of running the model with higher resolution everywhere. Therefore, you can see how this would greatly reduce the cost of Scream simulations if the user is only interested in one particular area of the globe. So the RRM functionality also comes with the ability to apply nudging weights. This makes it possible to nudge the coarse resolution region of your domain while allowing the high resolution region of interest to be completely free running. Therefore, this allows the user to specify the boundary conditions outside the region of interest from reanalysis or a pre-existing climate run, for example. Today, I will show a few examples of how Scream RRM can be utilized, noting that all these examples use the V0 version of the code. However, RRM is now fully functional in the V1 code as well. Also denoted here is a Confluence page, which serves as the official resource on how to make new grids, the links of which will be provided at the end of the presentation for reference. Next slide, please. So the first use of RRM was by former postdoc Wei-Ran Liu at UC Davis. In this pioneering experiment, she used Scream RRM to evaluate how Scream performs in simulating an extreme weather event, specifically the 2012 North American derecho, which was one of the deadliest and most destructive, fast-moving, severe thunderstorm complexes in North American history. In their example, the outer mesh was 25 kilometers, and they tested refined meshes from 6.5 to 1.6 kilometers, including Scream's default resolution of 3.25 kilometers. They found that Scream simulates the observed Bow-Ecker structure of the derecho well and predicts strong surface gusts that exceed 30 meters per second. And the agreement with observations generally gets better as the resolution of the refined area increases. They also found that Scream generally performed as good, if not better, than other models such as WRF, especially in terms of wind forecasts. Thus, this is a good example of using RRM to efficiently evaluate the ability of Scream in simulating an extreme convective weather event, and performing various sensitivity experiments, something which would have been costly to execute in the context of the global model. Next slide, please. Another example of using Scream RRM to evaluate weather extremes is atmospheric rivers. Here we display the Scream California RRM grid on the top right panel, which has 3-kilometer resolution over California and 100-kilometer resolution over the rest of the globe. The size of the refined mesh of this domain is much smaller than one would typically expect for a refined domain, because this exact grid was used for long-duration climate simulations, which will be shown in the next slide. So unlike the derecho event, of which the convection cannot be resolved by conventional GCMs, atmospheric rivers themselves are sufficiently resolved by models with resolutions of 100 kilometers, such as E3SM. What is not resolved by these models is the complex topography, such as that associated with California, and thus the topographically influenced precipitation distributions. Thus, we evaluate how Scream RRM simulates 4 meteorologically diverse atmospheric river events. Displayed here is a Category 5, or the strongest possible AR, that hit Northern California in October 2021. On the bottom left, we see that SCREAM has a seamless transition regarding the simulation of the AR, or IVT plume, as it traverses resolutions of 100 kilometers to 3 kilometers as it makes landfall on California. On the bottom right panels, we see that SCREAM has a good representation of the accumulated precipitation distribution, as it is able to capture the local maximum associated with topography, not only for the prominent Sierra Nevada mountain range, but also for the smaller coastal ranges as well. Though we do note a tendency of SCREAM to have an overactive rain shadow effect, as depicted by the wet bias over topography and dry bias on the lee sides, such as in the Sacramento Valley and in western Nevada. Nonetheless, SCREAM RRM exhibits good skill in simulating California atmospheric rivers. As previously mentioned, this exact grid was used to perform decadal length simulations. Next slide, please. And these simulations were performed by postdoc Jishi Zhang. So leveraging RRM, she was able to perform the first climate length simulation using the SCREAM codebase. So this is an example of how one can utilize SCREAM RRM to serve the purposes as a high-resolution regional climate model. While these simulations are still fairly expensive, especially when compared to running E3SM 1 degree, they are far more manageable and affordable than running SCREAM 3 kilometers globally. In this particular example, we took advantage of the regional nudging infrastructure and nudged the outer domain to an E3SM V1 future projection simulation. Specifically, we used the SSP 585 scenario that was originally run in E3SM by Shuai Zhang in 2021. Then 4 5-year segments from this 2015-2100 timeframe were selected and simulated. So the panel on the right hand side of the slide shows the average daily maximum summer temperature from E3SM on the top and SCREAM on the bottom, and illustrates that SCREAM can well represent the temperature patterns in California, which are highly influenced by the complex topography of the state. Thus, it has more added value in guiding infrastructure experts on potential localized climate extremes and preparing for the future climates, such as heat waves over the Central Valley. This is just one example of results, of which the full results are available on the GMD preprints, which are noted. Next slide, please. Another application of RRM is the ability to more efficiently perform so-called storyline simulations. This is where an extreme event is first simulated for the observed conditions and then evaluated to verify that the model has satisfactory representation. Then you rerun it for future conditions by increasing the temperature and greenhouse gases by the amount expected for a given time. Here we have an example provided again by Jishi Zhang, where she simulated the Beijing flood event from last year using SCREAM RRM and demonstrated that compared to observations, which are not explicitly shown on this slide, that the model performs well in replicating the observed precipitation amounts and distributions for this event. Then the simulation was rerun, assuming 2050 greenhouse gases and emissions with precipitation differences in the middle panel, showing that, in general, localized areas which were subjected to extreme precipitation amounts in the present-day climate, such as Beijing, could be subjected to further excessive precipitation amounts in the future from similar events. Though the warming can also cause the storms to shift, so some regions of future decrease are also expected. And just to note that the simulation utilized an interior grid of 800-meter resolution, which was only made computationally feasible by the utilization of using RRM. You've probably noted that many of the RRM studies in this talk used resolution finer than the standard 3¼ kilometer resolution. In most instances, this was motivated by the work done in Doubly-Periodic mode, which demonstrated that SCREAM does have good skill in representing cloud processes as the resolution is increased beyond the default resolution. And thus, it shows how these two configurations are complementary and how they can both be used to guide future resolution choices of the global model. Next slide, please. And finally, before I conclude, I just want to highlight that RRM grid development is very active. The Thread project alone is working towards adding many new grids at locations of ARM observing sites and field campaigns. This is primarily being done by Xian Ma. This will further add opportunities for expedited analysis of how SCREAM performs against observations. In addition, many of these RRM grids synergize as well, with cases being added to the DP SCREAM library and also helps to fill in the gaps of that configuration. For instance, the cacti and tracer field campaigns rely on the topography of the localized regions. For example, the purpose of the cacti campaign was to study convection over the complex terrain of the Andes, of which DP Scream cannot represent due to being a single point CRM with uniform topography. Thus, the RRM can fill the role of the efficient configuration for these instances where the less costly DP configuration is not valid. Next slide, please. So I hope I've convinced you that DP and the RRM configurations are useful and efficient frameworks for the analysis and development of Scream. And here are the promised links of resources that should get you up and running. For the DP Scream, this links to a GitHub wiki that provides one-stop shopping where you will be able to clone scripts and should get you up and running in a matter of minutes on any machine that E3SM currently runs on. For RRM, there are 2 links listed. The first documents the processes to be followed if you wish to make a new grid. From personal experience, I can attest that making a new grid requires a bit of a learning curve at first. This resource alone is certainly sufficient to achieve this goal. And if I can do it, anyone can do it. Trust me. So the second grid documents the RRM grids that have already been created and can be used today for science purposes. We encourage anyone who has already made a grid and scientifically validated it to please document that here so as to prevent potential duplicate work in the future. And thank you all for listening to me today, and I will be happy to take any questions at this point.
Okay, great. Thank you, Peter.